Hey guys, it's Miss Miklos, and in today's lecture we are talking about section 3.5, which is exponential models. And this is something that we are going to use for exponential growth, exponential decay, and compound interest. And you guys may or may not be thinking that logarithms are something that apply to your life. And what we're going to see here is that they actually do, especially I think in the sense of compound interest. If you are investing money, that's something that can be quite helpful as to knowing how much money you have. So I want to start here by talking about our equation. And we have this written in two different ways here. Okay, f of t equals a times e to the bt power, or we will also put it as y equals a times e to the bt power. I want you guys to notice that it's f of t. We're really used to seeing f of x, and what I want to stress to you guys is that the fact that t is there means that t is our input. And f of t, or y, it really doesn't matter what we use, represents the amount of something at time t, and that means t represents our time. And so we can kind of think of this as like our x and our y for this problem. And just like if we are finding the equation of a linear equation, even though x is the input, we still often need to find the slope or find the y-intercept. So that's why we also have these other values that we're going to solve for. A represents the initial amount, and we will see that that could mean the amount of the population as it begins. It could mean the amount of money that you invested, just depending upon the context of the particular question. B represents our rate, and I'm just saying that we need to remember that the rate should be a decimal value. So if they give us a percentage, we will have to go ahead and change it into a decimal. And last but not least, we have E, which is a number. Okay, we know that that is a number. It's approximately 2.7. And so this is the equation we are going to be using on every single problem today. So once again, y, or f of t, is the amount at time t, so t is time. B represents our rate, and A represents the initial amount. So you guys need to have this formula memorized. So let's go ahead and actually look at problem number 1. An Orange Lutheran athlete, let's call him Saul, as in our good friend Saul Garfunkel. If you don't know him, you're missing out. So Saul goes to the weight room for his conditioning class. When working out, he comes in contact with a bacteria on the handle of the 5-pound weights. Initially, there are 100 cells of the bacteria, and it grows at a continuous rate. After an hour, the bacteria has grown on his hand to 420 cells. Gross. Find an equation or model for the number of bacteria after T hours, and then tell Saul to wash his hands. Okay, so what are we actually having to do here? If we look at this, a lot of this information doesn't really matter, so I'm just going to go through and kind of highlight some things that I think are going to be important for us. So I don't think it matters what kind of weights. Good for him that he can lift 5-pound weights. That was a joke. So we know 100 cells. It says initially there are 100 cells. I'm thinking that would be important. The fact that there's 420 cells after an hour seems important to me as well. So I think I'm going to stick with those, and I'm going to go ahead and write y equals a e to the bt power. So we need to go ahead and write an equation for the number of bacteria after T hours. So if we are going through this, they're telling us that after 1 hour, there are 420 cells. So I'm going to say 420. And I know that our T value here is going to be 1. Okay, so y is 420 and time is 1. So we know this is going to be in terms of hours. It tells us that initially there are 100, so I'm going to say 100 E, and we don't know the rate. So I have B technically times 1 there. Or we could just write B. And in this case, that's all they're asking us to do is to go ahead and substitute in that information and find an equation. Now, in the future, we're going to have to go a step further and figure out how could we actually solve for the rate based on this information given to us. So this is just kind of making sure that we're feeling okay on how to actually input one of these, input this information into the equation. Number 2, Saul and his friend Larry decide to get a little manly with a game of pool. Being the alpha male and master of life that he is, Saul bets Larry 5 large, by the way, I didn't know what that meant, it means $5,000, that he can beat him on the elliptical pool table. Larry, of course, didn't see it coming, and Saul dominates the game. Don't forget, though, Saul just may be the sharpest knife in the drawer, so he takes that $5,000 and deposits it into an account, earning 2.1% continuously compounded interest. Find the amount of money in the account after 15 years. So guess what? Nothing up to this point matters. Okay, that's all just extraneous info. Things that matter: $15,000, 2.1%, continuously compounded interest, and finding the amount after 15 years. So let's fill in the information we know. The initial amount is $5,000. The total amount, that is what we don't know, so I'm going to write Y. That's what we're trying to figure out. That's our unknown value. The rate is 2.1% or 0.021, and the time is 15 years. So we know that our equation is y equals a times e to the bt power. So we're going to go ahead and substitute all of this information into this equation. So this time, we're trying to find y, so I'm going to leave y. Our initial amount was $5,000. We know e is a number, so I'm leaving it. And to the bt power, okay, we know that the rate is 0.021 times 15. And the beauty of this particular equation is that if I am trying to isolate my unknown value, I notice it is already isolated. So the way that we are going to answer this question is to put this straight into our calculator. Now, the biggest thing I want to stress is that we need to make sure that this entire thing is up in our exponent. So when I input that all into my calculator, we end up getting $6,851.30. And since we are in the U.S., it would make sense that we would round to 2 decimal places because we're talking about money. So now what we're going to do is we're going to use that information in problem number 2 and write the exponential model, finding the amount of time it would take for the initial amount to double, triple, and quadruple. And I'm hoping that somehow we find some sort of pattern here. So we know that our initial amount was $5,000. If it was doubling, that would make our amount $10,000. Our rate was 0.021. And in this case, we don't know the time because that was kind of our unknown value here. For it to triple, if it tripled, it would be $15,000 equals $5,000 e to the 0.021 t. Okay, and $15,000 would be if it tripled the 5,000. For quadrupling, it would be 20,000 equals 5,000 times e to the 0.021 t. I am messing up there. Okay, so I actually want to look back at this very first one and just kind of demonstrate something. If we notice, and we saw this in our notes on a previous lesson, my unknown value is up in my exponent, so we do know we need to change forms. The issue here is 5,000 is not being taken to the power, so I need to start by dividing both sides by 5,000, which would give me 2 equals e to the 0.021 t power. So notice I have a 2 when it's doubling. If I use that same method over here and divide both sides by 5,000, I get 3 equals e to the 0.021 t power. So triple, there we go, triple means 3. And you've guessed it, quadruple means it's going to be 4 equals e to the 0.021 t power. So this discovery actually shows us it doesn't matter how big our initial investment is, it's going to take the same amount of time for it to double. So that is something that can just be really helpful if we go ahead and know that, because sometimes they may not provide us with the initial amount, so it can be helpful for us to know that we can just write 2 if it's doubling, 3 if it's tripling, stuff like that. So for number 3, we're doing something similar. It tells us find the rate to the nearest 1/10 of a percent and identify if it is exponential growth or exponential decay. So number 3 tells us that a population of bacteria doubles every 15 minutes. So we're going to use the fact that it's doubling every 15 minutes and say 2 equals e to the 15b power. Okay, what 2 represents? 2 is really our amount divided by the initial amount, and that gives us that 2. So notice I do not need an A or a Y. That's what this 2 is representing. Now, to go ahead and solve this, for some of you, it might look better if we switch the order because we like things to be on the left side of the equation for some reason, but I just want to point out these mean the same thing. I'm going to change this into a logarithm. And if you would prefer to take a log of both sides, that's great. Just like we learned in our last lesson, you can use either method. But this would be ln of 2 equals 15b. So I'm going to have to do ln of 2 in my calculator and then divide both sides by 15. And I can actually do that all at once. It would just be really important for me to close this parenthesis. And I end up getting 0.0462 is B. Now, obviously, that is not our answer. I need to then take this decimal place and round it over 2 places, and I get 4.6%. So if we look at this, this is a growth because it is a positive percentage. And we actually could have figured that out by just reading the question. When it's talking about what the bacteria is doing, it is doubling. Okay, next, a population of bacteria triples every 10 minutes. So once again, we are not given an initial amount. And I want to stress that if we are given an initial amount, like in number 2 here, or actually this isn't even a number, we could solve correctly using either of these 2 methods. It does not matter. They are both correct. In this case, though, we don't know enough information to do that, so I'm going to have to skip and say 3 because it's tripling is equal to e to the 10b power. So to solve this, I'm going to do ln of 3 equals 10b, and I'm going to divide both sides by 10. Hopefully you're seeing why it's so important that we know how to solve exponential equations. I get b equals 0.10986, and when I move my decimal place over, I would get 10.98, which is 11.0, and once again, that is a growth. So we can see that percentage, that rate is actually really big. It's increasing quite rapidly. Okay, so our next one says the half-life. And some of you guys are familiar with this term, some of you are not. So to quote the famous source of Wikipedia, here is technically the definition of a half-life. A half-life is the amount of time required for a quantity to fall to half its value as measured at the beginning of the time period. While the term half-life can be used to describe any quantity which follows an exponential decay, it is most often used within the context of nuclear physics and nuclear chemistry. That is, the time required probabilistically for half of the unstable radioactive atoms in a sample to undergo radioactive decay. So half-life is used basically to describe a quantity undergoing exponential decay, and it is a constant value over the lifetime of the decaying quantity. And the key thing with half-life, it's very similar to if it's doubling or tripling. If we see double, we know it's a 2. If we see triple, we know it's a 3. With half-life, we know that we are going to start with 1/2 or 0.5. Okay, so that's just something we need to be a little bit familiar with. So I'm going to write 0.5 equals e to the 1620b power. And so right away, I'm thinking that our answer is going to be a negative value. And I'm thinking that this is going to be a decay. And in fact, when I read that definition, it said it is an exponential decay. But when I change forms, I get ln of 0.5 equals 1620b. And I'm going to divide both sides by 1620. And in my calculator, I get something that looks like this, negative 4.2786863 e negative 4. We know that this whole idea of e negative 4 means like times 10 to the negative 4th power. So I'm going to take this, move it over 1, 2, 3, 4. So we actually get b equals negative 0.00043. And the reason why I did this, it told us to find the rate to 5 places behind the decimal. So we're going to go ahead and leave it like that. Technically, if I was writing this as a percentage, I would say it's negative 0.043%. Okay, but we would most likely leave it like this. What we normally do with half-life, we normally actually then go ahead and apply this value to determine something. And I also want to stress you guys that whenever we think something is a decay, we do need to have a negative rate there. So it would make sense that a negative rate would be a decay. In 1990, at the prime of the career of the man, the myth, the legend, Barry Sanders, if you guys remember Mr. Hill, he wrote this, and he says, shame on you if you don't know who that is. And there he is for us. Detroit, Michigan had a population of 3 million people. However, when the king of the jungle, get it because he's a lion, retired, the team's performance went right down the tube. Detroitians abandoned the city with no regard. Don't judge them. Who wants to live in a city whose team goes 0-16? With no light at the end of the tunnel for the Lions, the projected population in 2015 is 2.74 million. Find the exponential decay model by letting t equals 0 correspond to 1990. Use the model to predict the population of the city in 2020. So once again, this is a problem where we have a ton of info. So let's go ahead and just kind of find the important information that we need. I think all this stuff at the beginning, the only thing that matters is in 1990 there are 3 million people. Everything else, we can just kind of forget about it. Who cares what their record was? Okay, other pieces of information, so let me even just highlight this anymore. It says 2015 is 2.74 million. And then it says find the exponential decay by letting t equals 0 correspond to 1990. And we want to predict the population in 2020. And this can be a little bit confusing, so I want to start by just putting some information down. We know that the initial amount is 3 million. The total is 2.74 million. And what's weird this time is we do not know what the rate is. Okay, B is our unknown. Now our time. This is where this whole concept of letting t equals 0 corresponds to 1990. We know the time is whatever time it is that it's 2.74 million. So technically, I'm going to do 2015 minus 1990, and that gives us 25 years. So we have 2.74 equals 3 times e to the 25b power. Now notice this has nothing to do with predicting our population in 2020 yet, and it brings up something really important, that whenever there are multiple things that we do not know, we always need to find the rate first. Okay? The rate is what is going to allow us to find what the population is later on. So I'm going to go ahead and rewrite 2.74 equals 3 times e to the 25b power. And I'm going to begin by dividing both sides by 3. So this is approximately 0.913, and I just want to remind us that we are leaving that exact value in our calculator like we talked about last class. When I change forms, I get ln of 0.913 equals 25b. And when I divide both sides by 25, I get negative 0.003626 is b. So if I'm rounding this to 3 decimal places, I would get negative 0.004 is our b value. And it's really important that we pay attention to what the directions tell us in terms of the b value. And believe me, on the homework and on tests and on quizzes, it will be very, very evident what you need to round to. Now, we need to go ahead and figure out, well, what is the amount in, or what is the population in 2020? Okay, so 2020 is 30 years after our initial amount. So I'm going to say y equals a times e to the bt power. And we're going to leave y because that's what I'm trying to solve for. Our initial amount was 3 million, and our rate is negative 0.004 times 30, because 30 is our time, because it's 30 years from 1990 until 2020. The beauty about this is that our variable is already isolated, so I can just put that in my calculator, and I get 2.66 million people will be living in Detroit at that time based on this exponential model. This would be a reasonable answer because since we have an exponential decay model here, it would be reasonable that our overall amount of people is going to decrease as well. News of an ecological disaster in Hungary is that a reservoir at an aluminum plant ruptured, causing a red toxic sludge to flood the area and seep into the soil. Towns have been evacuated and people are not allowed to return to their homes until the initial toxic levels of the soil have dropped to below the dangerous level for humans. After 12 years, the toxic levels have gone from 1,000 grams of toxic aluminum per square foot in the soil to 235 grams of toxic aluminum per square foot of soil. If the non-lethal levels of the toxic start at 240 grams per square foot of soil, how many more years do these towns have to remain deserted before they can rebuild? For this problem, use a rate rounded to 3 decimal places and find the year to the nearest whole number. Okay, so going through this, I went ahead and kind of highlighted the information that I thought was going to be important. And the first thing that kind of jumps out at me is that we don't know what a rate is. So I need to go ahead and I need to use the information of 12 years and 1,000 grams and 735 years, not 735 years, 735 grams to help me figure this out. So we're going to go ahead and say after 12 years, there are 735 grams. Our initial amount was 1,000 grams. And this was after 12 years, so 12 is our t-value. We do not know what the rate is. So I'm going to have to begin by dividing both sides by 1,000. And so I have 735 over 1,000 equals e to the 12b. We're going to go ahead and take an ln of both sides. Not of both sides. I'm just going to change forms here. And then divide both sides by 12. And I would really encourage you guys to practice putting this in your calculator. They told us to round our rate to 3 places past the decimal, so I get negative 0.026. This rate looks reasonable because my initial amount was 1,000. It decreased to 735. So now I'm going to use y equals ae to the bt again. This time we need to figure out how long is it going to take for it to get to 240. There's two different things that we can do here. We can go ahead and now say, it says how many years more. So at this point, there were 735 grams. And we know our rate is negative 0.026, and we don't know the time. We don't know how many more years. And the reason why I use 735 this time is because they're asking us from this point in time, how many more years is it going to take? If I used 1,000, I would have to, at the end, kind of factor in this 12-year difference into my answer. So I'm going to start by dividing both sides by 735. And then I need to change forms and do ln of 240 divided by 735 equals negative 0.026t. Divide both sides by negative 0.026. And I end up getting 43 years because they told us to round to the nearest whole year. So I would say that numbers 4 and 5 are really good examples of these two-step problems, where in order to figure out what they're actually asking for, we need to use the information given to find the rate first. That's why it's really important that we circle all the important info to make sure that we know exactly what we need to do. Our final problem deals with this chart. And I actually think that using continuously compounded interest is probably the most applicable thing for most of us. Most of us are not going to be like finding some sort of half-life for the rest of our lives or figuring out some sort of exponential population growth. But everyone at some point in their life will most likely need to deal with investments. So I'm not discounting those other things, but I think this is really important. So if we look, your homework has one of these as well. Problem number 6, all this info goes with 6. This goes with 7, 8, and 9. So this first column is our initial amount. Then we have the percent rate, the time to double, and the amount after 10 years. So we really have two different problems. These two columns are not connected to one another. They are two separate problems, okay? But I just want to remind us that first thing we should always find is our rate. In this case, we know the rate, which is awesome. So I'm going to go ahead and kind of zoom in here, and you guys are going to have to rely on your handout to kind of see the info. The first problem for number 6, it says the time it takes to double. So we could do this one of two ways. Okay, they tell us that our initial investment is $10,000 and that the rate is 3%, so 0.03t. And if it's doubling, that would give us $20,000. Or what you could have done right away is seen that double. And remember, it doesn't matter what our initial amount is. This would be 2 equals e to the 0.03 t. I want to stress these are both correct. Okay, in fact, if you use this method, our first step would be to divide both sides by 10,000, which gives me this equation. So if I'm solving this, I would have ln of 2 equals 0.03 t. So I'm going to do ln of 2 and divide both sides by 0.03. And I end up getting 23.1 is equal to t. So I'm going to go ahead and scroll up here and say that the time to double, and it told me in tenths, so that's why I said 0.1, is 23.1 years. Now, the second piece of information they give to us is how much money are we going to have after 10 years? So I'm going to say y, because that's the amount of money, equals 10,000 e to the 0.03 times 10. This time they're giving us 10, which is the input, and we're finding the output, which is y. The glorious thing about this is that y is already isolated, so I do not need to change forms. I can just input this into my calculator, and I get 13,498.59. So I'm going to go ahead and put that in, and I'm going to put a dollar sign because we know that this is money. And if we look, that does look like a somewhat reasonable answer. It would make sense that we have more money after 10 years since our rate is positive. Okay, moving on to number 7. Number 7, they give us the initial investment of 1,000, and they tell us it takes 12 years. We need to find the rate first. Okay, whenever we don't know something, we know we need to find the rate. So this is number 7. I'm going to start by using that fact that it takes 12 years to double, and I'm going to say 2 equals e to the 12b. Okay, so 12 is because it took 12 years for the amount to double. B is our rate. So when I change forms, I get ln of 2 equals 12b. I'm going to divide both sides by 12, and I end up getting 0.058 is our b value. So I'm going to go ahead and write 5.8%. And it did tell us to use the rate to the nearest tenth. So now that I have that rate, it's going to be a lot easier for me to figure out how much money is there going to be after 10 years. So our initial amount is 1,000. E to the 0.058 times 10. And once again, with the rate and the time, the order that we put those in doesn't really matter because we're multiplying them together. Once again, my variable is isolated, so I can just put that straight into my calculator and I get 1786.04. So I'm going to go ahead and say 1786.04. Okay, looking at number 8, they give us our initial amount and they tell us the amount after 10 years. First thing we need to determine, what is our rate? Okay, notice the pattern here. We always need to determine the rate first. Okay, so number 8, y, so 182,500 equals our initial amount of 100,000 times e to the 10b power. Okay, 10 years is because this is the amount of money after 10 years. B is the amount we do not know. So I'm going to divide both sides by 100,000. And so I get, I'm just going to reduce this. I know it reduces even more, but that's okay. 1825 over 1,000 equals e to the 10b power. So I'm going to change forms, and I have ln of 1825 over 1,000 equals 10b. I know then that I need to divide both sides here by 10, and I end up getting 0.060 as our b value. So that means our rate is 6.0%. Now that I know our rate, I can go ahead and figure out how long it takes to double. So I'm going to say 2 equals e to the 0.06 times t power. Okay, that 0.06 is our rate. T is because we don't know the time. I'm going to change forms and make this ln of 2 equals 0.06t. And I need to divide both sides by 0.06. And I end up getting 11.6 is our time. So you guys are noticing a lot of repetition here. And I'm going to go ahead and write 11.6 years. Lastly, number 9, we do not know the initial amount. We know the rate. We do not know the time to double, and we know the amount after 10 years. In this case, it honestly does not matter what we decide to solve for first, because the time to double is not dependent on our initial amount. So, let's go ahead. There we go. Lost track of where I was. So for number 9, let's find the initial amount first. So we know after 10 years it is $1 million equals A, because we don't know the initial amount, times E to the 0.035 times 10 power. 0.035 is the rate, 10 is our amount of time. So this time, what I'm going to do is look and see what is my variable. And this is unique because our variable is not in the exponent. This entire value is just a number. So what I can do, I can divide both sides by e to the 0.35. That's what I get when I multiply these two numbers together. And I am left with A. So in my calculator, if I do 1 million divided by e to the 0.35 power, I get 704,688. Okay, and it told me to round to the nearest dollar, so that's what I did there. So I'm going to go ahead and write 704,688. Okay, now I'm going to find the time it takes to double. And as I said earlier, we could have done that independently and done it first because these two answers don't depend on one another. So the time to double equals e to the 0.035 t power. So I'm going to do ln of 2 equals 0.035 t, divide both sides by 0.035. And I end up getting 19.8 is the time. So I'm going to write 19.8 years. Okay, so this is everything we just kind of learned zoomed out here. So we can kind of look at this information, and the nice thing about this chart is it really goes through all the different scenarios. We had to solve for T, we had to solve for A, we had to solve for Y, we had to solve for B. Notice the only thing we don't try and solve for is E, because E represents a number. So I know this lecture was long, but hopefully seeing all these examples helps us to see how exponential growth and exponential decay are relevant in our everyday lives.